Hello, and welcome to this online presentation. My name is Romain Saki. I'm a postdoctoral researcher at the Polscher Institute in Switzerland. More specifically, I joined the Technology Assessment Group about 2 years ago. The Technology Assessment Group has a focus on the assessment of technologies from an environmental, economic, social, and risk perspective. Today's presentation will be about global energy system models and life cycle assessment. Global energy system models are part of the family of integrated assessment models. These are models that project the state of the world in the future by giving us a certain number of environmental and economic and energy indicators most of the time. It is a very appreciated tool because it allows to give projections following different scenario pathways. For example, if we project a world in which we don't do so much effort in reducing greenhouse gas, or on the other hand, if we project a world in which we are very ambitious about limiting greenhouse gas emissions. On the other hand, we have life cycle assessment. It is one of the many tools used in the industrial ecology community. Now, life cycle assessment has a different scope than integrated assessment model. It is very much process based, where we will assess most of the time the environmental performance of a given technology or system in a given setting. At PSI, we try to develop tools that can potentially combine the best of both worlds, and this is what this presentation is about. Now, why would we want to combine integrated assessment models and life cycle assessment? Maybe a way of answering that question would be to first look at the simple life cycle assessment of a passenger car. It is here shown on this slide. The life cycle of a passenger car would typically include the manufacture of components and their assembly into a car. The car would be shipped to the market of use. We would have to model some sort of energy chain to fill the tank or to charge the battery of the car. We would also have to model the construction and maintenance of road infrastructures, some maybe maintenance and repairs for the car along its use phase. And finally, we would also consider the disposal of the car, where the vehicle would be dismantled and different material fractions would then follow treatment or recycling channels. So you could see on the right that basically our model would be divided grossly into the foreground model and the background model. In the foreground model, this is where we would model our car, its driving performances. We would also design which components it is made of, the size and its mass, etc. And in the background model, we would have inventories about raw materials, the way they are extracted and transformed and supplied to, for example, the assembly plant. These materials and different services and goods are associated themselves to environmental impacts, which allows us to then back calculate the overall environmental impact of our car, which would then be typically normalized by the number of kilometers it would drive along its use phase, so that we obtain environmental impact per vehicle kilometer. The description of the life cycle of a passenger car I've just given you was somewhat simplified. In reality, in order to assess the life cycle performance of a passenger car, you need first to assess the life cycle performance of all the goods and services that are directly or indirectly involved with the life cycle of a passenger car. So, for example, if some components need to be manufactured and transported to our assembly plant, it is very likely that some lorry transportation is involved. In the same way, if our car needs some electricity either for the refining of the fuel or for charging the battery, it is very likely that some power plant will be indirectly involved, and it could be a fossil power plant or it could be a renewable power plant like a wind turbine. In the same way, although the example might seem a bit far-fetched, there could be some web browsing for all we know in the life cycle assessment of a passenger car. It could be that the car's owner at some point will look up some local mechanics using his computer, or it could be that some web browsing was involved in manufacturing a wind turbine or a truck. Um, the point of this slide is really to show that their respective life cycles are in fact interconnected, and if we are to pretend to calculate the environmental footprint of that car, we need first to resolve the whole system to see what is connected to what, and to calculate the environmental footprint of all these life cycles first, so that we are able to have our final answer as to the environmental footprint of our passenger car. If we look at the life cycle of a typical car equipped with an internal combustion engine, it would probably look like what is being shown to you on this slide. We have the manufacture of components and their assembly. Then we would, following a given driving cycle, calculate the energy and therefore the fuel consumption of the vehicle. We would include some maintenance and component replacement steps, and then we would account for its disposal. And if we look, for example, at how this is distributed in terms of CO2 emissions, typically about two-thirds of the overall emissions would occur during the use phase where the fuel is being combusted. Another 13% would originate the manufacture of the components, and roughly another 13% would originate from the extraction and the refining of the fuel, and the remaining percentages would be spread across the other life cycle phases. Now, from a data and model quality and robustness point of view, this is very good news, because it means that about two-thirds of the impact we calculate originate from a phase for which we have a very good documentation. The fuel economies of current and past and even future cars is rather well documented, and so we can calculate with a certain level of confidence the CO2 emissions of the vehicle. And well, we have another third left that is located more upstream in the supply chain for the manufacture of the components. And this is why here I've placed an arrow on the left showing how we go from what is very certain, what can be measured with quite some confidence, to what is less certain as we go upstream the supply chain or in our background database. But things change a little bit when we start to look at novel powertrains, like electric powertrains that would involve battery electric vehicles, but also fuel cell vehicles or plug-in hybrid vehicles. While the structure of the life cycle wouldn't necessarily change, we would observe some change as to how emissions are distributed. While we previously had two-thirds of our emissions coming from the combustion of fuel, here obviously we do not have this combustion process because the car is running on electricity. And in practical terms, that means that most of the emissions go from the use phase to actually being emitted upstream the supply chain. And from a data robustness and quality point of view, this is a little bit more problematic because it's a little bit farther away from us and farther away from the use stage of the car for which we had good documentation. And suddenly we start to realize that it's very important to have good knowledge about these energy chains, these energy systems, not only today, but how they will evolve in the future. Besides the energy chain, so the emissions related to generating electricity, we would also notice an increase of emissions related to some of the components of the car, and one of those would be the manufacture of the battery. Here again, batteries can be produced in remote locations, for example Asia, and it's not always easy to obtain data. So this slide is really here to show that most of our emissions have now migrated from this certain um, um, uh, data area part of the slide to a more uncertain area. If we compare results for conventional and alternative powertrains for passenger cars, and in regard to greenhouse gas emissions, then results would typically look like this. The two bars on the left are electric powertrains, so battery electric and fuel cell vehicles, and the remaining bars from there to the right are conventional powertrains, with the exception maybe of plug-in hybrid vehicles. Um, for those conventional powertrains, we clearly see that the share of direct exhaust emissions, so the combustion of the fuel, clearly represent, as we previously mentioned, about 2/3 of the overall impacts. And this is, of course, to be contrasted with the two vehicles on the left, for which most of the impact come from the energy chain. Again, this really reinforces into um, trying to investigate a little bit more those energy chains and energy systems if we want to be accurate as to the environmental footprint of these novel powertrains. That was the first point, and the second point maybe is to say that as car gets cleaner, as they have more efficient engine, the share of fossil fuel combustion will reduce, and the same can be said for these novel powertrains. As the electricity used to charge the battery or to produce hydrogen gets cleaner, the share of energy chain will also reduce, which will make some other source of emission look comparatively bigger. And here I want to mention emissions associated to the glider production of the car and its powertrain and its energy storage. And that is exactly the second point of this slide, to say that we should also investigate further how these components are made, and more precisely how the raw materials that enter the composition of these components are made, such as aluminum, steel, and so on and so forth. And this is a slide maybe to finish on the topic of passenger cars. This slide has two graphs, and I would like that we focus on the graph on the left, which shows how the greenhouse gas emissions of these cars per vehicle kilometer will evolve as we modify the greenhouse gas intensity of the electricity used in the system. So basically, we have a few horizontal lines, which are our fossil fuel vehicles, for which the life cycle greenhouse gas emissions is rather insensitive to how carbon intensive the electricity is. And then we have battery electric and fuel cell cars, which are on the opposite, very sensitive to the carbon intensity of the electricity. That would be the yellow line and the dark blue line. It is to note that the fuel cell car runs on hydrogen produced by electrolysis, therefore very electricity demanding. And then we have a couple of other lines which are actually conventional powertrains but running on synthetic fuels, which are also very electricity demanding. So here it is clear that the greener the electricity grid becomes, the more performant these vehicles will become, as in contrast to conventional powertrains using fossil fuels. And we have, for some of these vehicles, at some point, some break-even points above which they start to deliver net greenhouse gas emission benefits. So that was the first important point here, to be to better investigate our energy systems, but also we see that when the carbon intensity of the electricity is very close to zero or even reaches zero, we still have quite a bit of residual emissions. For example, we can see here for the electric car that we have about 100 grams left of residual emissions, and those emissions are actually associated, as we've just seen in the previous slide, to the production of the glider, the production of the battery, the production and maintenance of the road, etc. And so all this brings us to the point of this presentation. If what happens very far away from our car and from the point where it is used is increasingly important, meaning the way we produce electricity and the way we produce the raw materials that will enter the manufacture of batteries, fuel cell stacks, and so on. Is there a way to improve the quality of their modeling? Well, at PSI, we seem to think so, and one of the ways would be to combine integrated assessment models with the database we traditionally use for life cycle assessment. Now, on this slide, I try to compare both worlds. On the left-hand side of this slide, you have the world of integrated assessment model as I picture it. It is a very comprehensive model where the whole world is represented, and it is, though, composed of structurally gross networks of industries and industrial activities, residential transport activities, but that covers rough regions of the world. So usually you would have somewhere between 10 and 20 world regions. That would depend on the integrated assessment models. And for each region, the model would give you production output volumes and for different number of activities. And of course, the detail for there will be different levels of details for these sectors depending on the specialty of the integrated assessment model in question. But you would usually have represented the power sector. So for each region, the model would give us how much of each technology is producing in terms of electricity and the efficiency of those power plants. It would also give us the share in terms of fuel production, how much of each type of fuel is produced, but also who consume each of these fuel types. We would also have maybe some indicators for metals, how much metal of each type, of each rough type, like steel, aluminum, and so on, is used. And maybe sometimes they would also give us how much of it comes from secondary or recycling channels. And also some IAMs would give us a picture of a representation of the transport sector by telling us how is the transport demand expected to evolve in the future, what would be the composition of passenger cars in terms of powertrain size, and the same for road freight transportation, and so on. And of course, the whole idea of integrated assessment model is that they give us these rough pictures of the world, not only for today, but also for the future. Some go as far as 2100 or 2150 even, although we need to be a little bit cautious as to how able is a model to predict the world in 100 years from now. But nevertheless, it's very interesting to do projections. And of course, the IEM model will produce these projections helped by an optimization engine who will be receiving a set of constraints in terms of costs, but also in terms of, for example, greenhouse gas limits not to overcome. And so we can have different projections following different narratives. So to say, as I mentioned at the beginning of this presentation, we could have projections for a baseline scenario where the greenhouse gas emissions are just left to be conditioned by market rules, or we could have a world in which We have a lot of state intervention to try to limit greenhouse gas emissions as much as possible, but also certain scenarios where different technologies are pushed, like carbon capture and storage and so on. And on the other side, we have the world of life cycle assessment. So PSI is a important contributor to the EcoInvent database, which is probably nowadays the most comprehensive and transparent database to be used for LCAs. Um, now, the the regional distribution of data in EcoInvent is much more uneven, and it very much reflects how much each of the region is contributing to populating the database. So we would have very detailed and varied data for a large number of industrial processes in Switzerland and to maybe a lower extent to Europe, but still very well documented. And then we would have some inventories for some other processes. Um, but much more dispersed around the globe. For example, we would have inventories for mining extractions in South Africa, a little bit maybe on agricultural production in South America, and also some data sets in Northern America and the Quebec and Quebec region and Canada. Um, but the variety of industrial activities doesn't is very um, much higher than what we have in an integrated assessment model. We have activities description for fuel production, for the production of plastics and various chemicals, for the production of textiles, for fishing and agriculture, the production of different metals, and even within a certain metal, subcategories of metals. For example, for steel, we would have regular steel, low alloy steel, stainless steel, and so on. So the idea when we talk about combining integrated assessment model and lifecycle assessment is really trying to extract the best of both worlds and hopefully obtain some sort of representation of the world today and in the future with a comprehensive data coverage, but at the same time with a pretty high technological resolution. In order to achieve such combination between integrated assessment model and life cycle assessment, we have developed the last couple of years a certain number of tools that we use regularly. So we work mainly with three types of integrated assessment models, which are Remind, which is developed by the Potsdam Institute for Climate Impact Research. Um, then we have Image, which is a model developed by the Environmental Agency of the Netherlands. And then we have STEM, which is a model developed here at PSI with a focus on Switzerland. We have developed a tool called Premise, and Premise's role is basically to take in the output projections of such models on one hand, and also take in on the other hand EcoInvent, which is our lifecycle inventory database. And thanks to a number of tools, we'll try to do the merging between the two of those. Um, some of the tools Premise will use are Wurst, which is also developed by our colleague at PSI, Chris Mutel, um, to allow for the fast handling of database under the form of Python dictionaries. Then we would also use a certain number of inventories in order to add potential new technologies that might appear in the future. And then also some other tools like calculator that allows us to add inventories for future mobility systems like future passenger cars, future trucks, etc. So Premise will combine EcoInvent with this integrated assessment model, and will output a new EcoInvent database which has undergone a certain number of transformations. Depending on this, of course, on the energy scenario that was taken in on the left side, we would end up with EcoInvent database that reflect that energy scenario. So we could have, for example, EcoInvent database for any time in the future, usually between today and 2050, with, for example, a baseline scenario where nothing much is done for the environment. Let's put it that way. But we could also have an EcoInvent version of the future where, for example, everything is done to respect the Paris Agreement targets. That is, I believe, somewhere around 1.5 degree of atmospheric temperature increase. We could also end up with a database where there is a strong push incentive to develop carbon capture and storage at the power generation level or cement or steel production. But we could also have a database that reflects a world in which the production of biofuel is maximized. Once we have the desired modified database, then we can use another tool developed at PSI, Brightway, which is an LCA framework, and we will use that tool to calculate some environmental indicators for whatever system we're looking at. A car, a megajoule of a certain fuel, or a kilowatt hour of coming out of a certain technology. And then we can produce some indicators, for example, in terms of CO2, or in terms of metal resource depletion, or fossil resource depletion. What we are working on now currently is to try to have this feedback loop in which these environmental impact indicators that we've calculated with Brightwave would be somehow considered back into the IAM model. Whether it is during the IAM optimization calculation or within, or whether it is considered afterwards is still a question we need to answer. But it is definitely one of our objectives today to try to close that loop so that LCA can help integrated assessment models being better and also add not only CO2 as a constraint for the optimization engine, but maybe also constraint in terms of other environmental indicators like particulate matter and these kind of things. We have seen that Premise is somewhat a central tool in that workflow we have just presented on the previous slide. But what does Premise do exactly? Well, Premise does already a number of things, and then there are some things it is about to be doing, and then there are some other things that are just on the to-do list for now. Today, Premise is able to do four things mainly displayed on this slide. So right now, Premise can adjust electricity market in our EcoInvent database by reflecting the projected development of renewables or nuclear or other kind of technologies. It will also adjust the efficiency of those power plants depending on the year we're at and the energy scenario we are following. Recently, it has also allowed us to adjust the efficiency of photovoltaic panels, which was not so well represented in the original EcoInvent database. And that is extremely important when we look at very ambitious scenarios in which solar power represent a big share of the electricity produced. You really want to have the efficiency correctly set there, because otherwise you end up with underperforming solar panels that will have overestimated metal resource depletion impacts. Another thing Premise does now is to adjust the efficiency of certain industrial processes. This is notably the case for cement, where we will adjust the clinker production energy efficiency. We will adjust the fuel mix that will be used in the future, and we will also adjust the clinker to cement ratio in different parts of the world. We also do that to a certain extent for the steel production, where we adjust the efficiency of the furnace, the electricity that is of course used to produce secondary steel, but also the share of primary versus secondary steel that should be available in the future, and depending on the regions, of course. Another thing that Premise does is it deploys carbon capture and storage solutions wherever the IEM thinks this would be the case in the future. So mostly for now, this occurs at the power generation level, but also at the cement production level. Now, there are three other items that are on the good way of being completed very soon. The first one will be the transport sector. So with Remind in particular, we are receiving fleet projections for passenger cars and trucks. Based on this fleet projection, Premise will build fleet average passenger cars and trucks for the year we are looking at. So it will consider novel powertrains, their efficiency, and also the different shares, fleet shares for different sizes and so on. And it will substitute the existing market for passenger transport and freight transport, and link back to activities in the EcoInvent dataset that consume such transport services. This is actually quite a big deal for the lorry transportation, which is very present across the database. Another thing Premise is about to be doing, or that is soon to be implemented, is the adjustment of hot pollutant emissions across the different industrial activities in EcoInvent. To do that, we are using projections from the air pollution model GAINS, which tells us how different emissions, substances, which are non-CO2 substances like sulfur dioxide, carbon monoxide, this kind of emissions, how will those evolve for each industrial sector in each region of the model, and for anywhere between current years to 2100, I believe. And so we will adjust all these non-CO2 emissions across all the industrial activities of EcoInvent. And finally, Premise will soon implement another module that will create new fuel markets for all the activities that consume liquid fuel and gaseous fuels for all the regions of the IAM model, and for which we will have the respective shares of traditional fuel, biofuel, and synthetic fuel. And of course, these new fuel markets will link back to the transport sector. It will link back to basically anything that consumes fuel. And then on the to-do list, we have that last item that concerns metals recycling. Here the idea is, of course, to project to which extent some of the metals that are extensively used in renewable plants, but also in mobility associated to the manufacture of battery. So to which extent those metals will be recycled. And so in order to reflect the amount of the recycled content share in any amount of metal that enters the composition of batteries and wind turbines and electric motors. This will be extremely important because right now current models for batteries, even when prospective, they generally assume that all new metals entering the composition of the battery is from primary source, while we have good chances that in the future a substantial share of that will come from recycling channels. Is Premise really used? Yes, it is. We have used it in a few projects now. Maybe we should start by this one. PSI and the Technology Assessment Group and the Laboratory for Energy Analysis altogether is involved in a project called SCCER Mobility, and during that project we use premise and we use the concept of integrating integrated assessment models into LCA, via premise. And in particular, we integrated the the PICS model Remind together with PSI's model STEM. So Remind as a global scope, and within that global scope, it has different world region, one of them being Europe. And within the Europe region, we have, of course, Switzerland, which was then um, represented by the STEM model. So technically speaking, we embedded STEM in Remind and doing the connections wherever needed. And then we did so to compare the environmental, economic, social, and risk um, uh, performances of different means of transport. We did that for the current setting in Switzerland, and but we also did that for the year 2050. There we had three major scenarios at the Remind level. So at the global level, we had a 1.5, 2, and 3.5 degrees of atmospheric temperature increase scenarios, so from best to worst. And we aligned that with three domestic scenarios for Switzerland. Um, so from best to worst, that would be a net zero CO2 scenario, a minus 80% CO2 emission scenario compared to 1990 levels, and a business as usual scenario. Um, this allowed us to do an assessment at the technology level, so at the vehicle level, that is. But also we did a fleet analysis, and we were able to combine in that way life cycle assessment with impact pathway assessment, environmental monetization. We were able to calculate cost of ownership and risk indicators for those, and also we were able to produce a few indicators related to utility of those vehicles. But we also used premise and therefore the concept of linking IAM to LCA in a few other studies. Um, Here is a list of them. The first one is Calculator, which is a tool we developed to do LCA of passenger cars, not only LCA, but prospective LCA of passenger cars. And of course, so this model will model the performance of cars today and in the future, and it will link to a database created by Premise, and so we can obtain LCA indicators for different types of passenger cars, whether we think the future will be bright or whether the future will be dark. In the same spirit, we also developed a calculator truck that corresponds to the second item on this list, for which we have a pending publication. There again, it's a calculator truck provides or produces LCA indicators for trucks, and for now and for the future. And again, the database used behind to produce the steel, to produce the aluminum, to produce the metals that will enter the battery composition, and so on and so forth, is a database produced by Premise by combining it with the Remind impact assessment model, integrated assessment model, sorry. Then we have two other studies, one about synthetic fuels and another one about nonlinearity in life cycle assessment. So Premise is a very practical tool that we see of a good potential to be applicable in a large number of studies as soon really as we need to evaluate the future performance of any systems really. But in practical terms, what does it mean? How useful is it really? Well, I think it is maybe time to go back to our initial topic, which was passenger cars. And I think it is not difficult to actually see the usefulness of that tool. So in front of you, you have a bar graph showing greenhouse gas emissions of a large electric vehicle operated in European conditions between 2015 and 2050. You will see that those bars are divided in three segments. And actually, the bars on the left are LCA results, so greenhouse gas emissions per kilometer, uh, where the background database is static. It means it's EcoInvent in its original form. Of course, we see that the battery electric vehicle reduces emissions over the years, and that is mostly due to our projection done in the foreground model, where we project increase in engine efficiency, in energy density of batteries, and so on. And you will see that the segments, the blue, yellow, and green segments that are really concerned with the emissions associated to building the car, building the batteries, you will see that those remain quite static. And that's because their emission is driven by by the extraction of certain metals and the production of steel, which in this case remain static. So the performance of, for example, the efficiency of producing steel in 2015 is exactly the same as that of 2050. But in the middle and right section of this bar graph, we there use dynamic backgrounds produced by premise. In the middle, we have a background that reflects a world in which we don't really do much about greenhouse gas emissions. We just let the market decide. And of course, this still leads to improvements, but taxation on CO2 is somehow very moderated, so it's not always the most beneficial technologies that um, um, gets the largest market shares. But nevertheless, we see that emissions associated, for example, to glider production, so blue segments, and also to some extent the energy storage, starts to change over the years, slowly, but we can visually see it. And then on the right segment, we there follow a very ambitious scenario where we try to keep the atmospheric temperature increase below 2 degrees Celsius. This involves in the background a certain amount of carbon capture and storage. It involves quite a high taxation on CO2 to promote some CO2 efficient technologies and so on. And there we see that it has a dramatic change on the CO2 emissions associated to building the glider of our passenger car. So we can really see that it adds another depth to our model by really considering what is happening in the rest of the world outside the product system of our passenger car. There are, though, a few limitations when you try to combine integrated assessment model to life cycle assessment. I do not pretend to list them all, and I might forget some important ones as well. But those that come to mind are maybe the following. We first have a problem at the level of geographical resolution. We have very large and gross region on the IEM side. Europe would be a region, North America would be another one. But on the other end, in our EcoInvent database, we often have inventories defined with a national scope, for example, France, Germany, Switzerland. So, of course, it is very rare to find a one-to-one correspondence, and we often have to deal with one-to-many correspondences in terms of geographical regions. So we have to deal with that. We need to make averages, we need to weight the importance of certain production volumes by any means. Um, and also another challenge comes from when we try to embed a integrated assessment model that has a national scope like STEM or TIMES into a larger one like REMIND or IMAGE. We also have some geographical gaps in EcoInvent. For example, we might have inventories on fishery, um, fish preparation processes for Norway, let's say, but the IEM tells us that there's going to be, I don't know, quite some activity um, occurring in Asia, but we don't really have the inventory for that. We just have inventories for Norway. Um, of course, this is a totally random example, but that shows that we need to find workarounds. How do we approximate the performance of a fish processing plant in Asia when we only have data about Norway? And there are, of course, several ways of going about this. Um, then, of course, there is the issue of the technological resolution in these integrated assessment models. One comes to mind would be steel production. Um, Steel production is probably as specific as it goes when it comes to IEMs, but of course, uh, we know that there are very many categories or subcategories of steel. We have steels with different content of carbons. We have stainless steel, recycled steel, but so we have to deal with this one-to-many correspondence here as well. Um, and this can be a bit problematic because, of course, the impact of producing low alloyed steel is very different from the impact of producing stainless steel. And of course, there are a few incoherencies here and there when you look at integrated assessment model numbers. Sometimes you find some funny efficiencies, and even the developers of those models are having a hard time explaining them. But this also goes as well for the CoInvent database, which is, full of errors, but on the overall very transparent, so it's quite easy to spot them. Finally, all the tools we develop are open source. Here are a few I mentioned. So I mentioned Brightway 2, which was a tool mainly developed by my colleague Christopher Mutel. And then we have Premise, which was pretty much the point of this presentation, and Wurst that you can also find on GitHub. And also we mentioned LCAs of passenger cars. And so calculator was the tool used to produce these numbers. We believe in transparency, and we believe this is also a very effective way of making our code and algorithm um, more safe and accurate by having many people to scrutinize them and suggest improvements. That was it. Thank you for staying with us up to that point. If you have any questions on what I've just presented, if you would like to use Premise in your own work, and if you'd like some advice on how to use it, or if you'd like also to suggest some collaboration, do not hesitate to write to us, either directly to the Technology Assessment Group or to myself. My email address is shown on that slide. Thank you very much.